Hey, good morning, guys. Today is Wednesday, March 25th, and we are going to move on and start Chapter 3. So, Chapter 3 is a little bit more of an applications type chapter where maybe we're not going to learn quite as many new or unique differentiating skills, but we're just going to apply the ones that we already have to doing some different things, okay? I think that this first section will be relatively smooth and easy. You can see here that kind of my plan from last year was to just print the notes for you guys. So I'll go ahead and put a copy of my notes on Google Classroom for you. But it's going to be pretty quick moving if we just go through these, and then I actually work out 3 examples for you once we're done. Okay, but hopefully you can see these all right. And we'll just kind of talk our way through them. So section 3.1 is increasing. It talks about increasing and decreasing functions. So literally what that means, an increasing function is just simply a function whose graph moves up as x moves to the right. So literally that's a graph that's going up from left to right. That's what we categorize as an increasing function. And then a decreasing function is just the opposite of that. It's a graph who's going down from left to right. And we're pretty familiar with that just based on the fact that we interpret data left to right, we read left to right. So we would say that if a graph is going up as you move to the right, it's an increasing, and if it's going down, it's a decreasing, okay? So what we're going to be doing is we're going to be literally describing when a graph is going up versus when it's going down from left to right. But obviously what we're going to do is it won't be that simple or that easy. We will be doing it without actually seeing the graph, okay? So what we're going to be doing is we're going to be running a test, okay? A test for increasing and decreasing functions, and basically it relates directly to the derivative. If you think about it, what the derivative is it's a slope function. Well, we know that when slope is positive, if you take the slope of any line, if a line has a positive slope, that means it's going up. Its rise is positive, okay? And if a slope is negative, that means it's going down because its rise is negative. And to rise negative means to go down. So obviously, a graph's increasing versus decreasing nature is directly related to the slope of its tangent line at that specific spot, which relates to its derivative, okay? The derivative is the slope function, okay? So there's kind of a lot of stuff in here, but most of it is semi-arbitrary. It says test for increasing or decreasing, let f be differentiable on an interval. So obviously, in order for a graph to be increasing or decreasing over a specific interval, it's got to exist over that interval, which means it's got to be differentiable. It says if the derivative is greater than 0, that means positive, it's increasing. We just said that. A line with a positive slope is going to be categorized as increasing or going up. If it's less than 0, meaning negative, it means it's going down. Again, negative slope is a line that's going down. And if it's 0, if the derivative is equal 0, that means its slope is 0, which means it is going to have a horizontal tangent line. It has peaked. It is either peaked or valleyed at that point. It's an extreme, a maximum or minimum. Okay, so you can see here just super simple stuff. This parabola is decreasing on this interval and then increasing on that interval. This parabola is doing the opposite. It's increasing from negative infinity up to 0 and then decreasing from 0 to positive infinity. This is kind of looks like a V-shaped absolute value graph. It's decreasing on this interval and then increasing on that. So decreasing from negative infinity to 0, increasing from 0 to infinity. And then this is a rational function where the equation is a fraction with x in the denominator. This curve is forever decreasing. This curve is forever decreasing. So it's decreasing on both intervals in that one. Okay. Moving on, basically what we're going to be, and this is going to kind of just talk about the work that we're going to do in just a hot second. It says definition of a critical number. A critical number is basically a point where the increasing or decreasing nature of a graph changes. So it says if f is defined at point C, then C is a critical point or a critical number if the derivative is 0 or the derivative is undefined. So if you think about that, like look at this parabola. At that point right there, at that vertex, the point where it stops decreasing and starts increasing, that would be a horizontal tangent line, which means it would have a slope of 0. Same thing right here, a slope of 0. This would have an undefined slope, and then same thing here. There's an undefined slope, there's a non-existing slope at that specific spot. So basically, a critical number is when the value of the function's derivative either is 0 or does not exist. Okay, and then down here it says guidelines for applying the increasing or decreasing test. The first thing we're going to do is, if we're going to be interpreting the derivative, we need to find the derivative. The next thing we do is we use our derivative to locate critical numbers of the function, meaning of its graph, and use them to determine our test intervals. So like up here, the interval would be -infinity to 0, 0 to infinity, where 0 is the critical number, because 0 is when it stops decreasing, starts increasing, right, along our x-axis. And then here's kind of the part that's going to be really easy for us. It says test the sign of the derivative at an arbitrary number in the test interval. That's going to make more sense once we get into and look at our 3 examples. And then it says use the test for increasing and decreasing functions to decide whether it is increasing or decreasing on the interval. I know that's kind of a lot of information, and when we get into these testing descriptions, it gets a little bit murky in terms of it seems simple, but I don't even really know if I understand what exactly he's saying. So let me show you a couple examples here of what your assignment's going to look like. Here are 3 functions. Okay, the directions say find the open intervals on which the function is increasing or decreasing. So just like on those graphs we saw, figure out where the function is going up and where it's going down from left to right. So that test that we just saw, step number 1 said find the derivative. So the first thing we're going to do with this polynomial function for number 1 is we're going to find its derivative. The derivative of a polynomial is crazy easy. We just use the simple power rule. 3x squared minus 6x plus 3. Okay? Easy enough. There's our derivative. What we need to do now is we need to find our critical numbers. Our critical numbers are, like I showed you here, our critical numbers are the maximums and minimums in a lot of cases. At every maximum and minimum, it's going to be a horizontal tangent line. Horizontal tangent lines have a slope of 0. Well, this is the derivative function. This is the slope function. So what we have to do is we have to find the values for which this derivative is 0. So literally what we do is we set that derivative equal to 0, and in the case of a polynomial, we factor. Okay? We can undistribute 3 from all those. We get x squared minus 2x plus 1 equals 0. So we have the 3 factored out on the outside. And then in here we have a factorable polynomial. This is a perfect square, this is a perfect square, so here's what we got. X squared factors into x and x. Positive 1 factors into -1 and -1. Why did I make them negative? Because they have to add to -2. The 3 really doesn't matter. So if we think about this for a second, I set my derivative equal to 0, which means I set my slope equal to 0. And then I solve for the x values that will make it equal 0. These are the x values where my slope is 0. So if you think about this here, the only one we have, the only critical number, this is x equals 1, and so is this one. So really there's only one critical number. It's x equals 1. Okay? Usually, and what's going to happen on your assignment is there's going to be other ones. Okay? There's going to be more than one critical value. Okay? This means that in this instance, that's the point, either it's a maximum, a minimum, or a point of inflection. Okay? What it's going to be in this case, and this is kind of the third step, once you solve for your critical values by basically setting your function equal to 0 and solving for x, that is going to be what splits apart your domain. So my domain now, from -infinity up to +infinity, is going to be split at only that one critical number, which is +1. Okay? So to recap, take your function, find its derivative. Set the derivative equal to 0. That's essentially setting your slope equal to 0. Solve for the x values that make it 0. Those are your critical values. Those are the numbers that split your domain into your different points where it's going to be potentially either increasing or decreasing. All you have to do then is plug a number in that test interval back into your function, back into your derivative, excuse me. If you plug a number into your derivative, you're just testing to see if it's going to be a positive or negative. So all I'm going to do here is I'm going to take the easiest number in this interval, which is 0, plug 0 back into your derivative. If you plug 0 in here, that wipes it out there, wipes it out there. It's 0 minus 0 plus 3, which is positive 3. That means that the derivative, your test number, gave you a positive result right there. A positive slope means that the function is increasing from negative infinity to 1. Every number from negative infinity to 1, if you plug it back into your derivative, is going to give you a positive derivative, which means it's a positive slope, which means it's going to be an increasing value. It's going up from left to right because it's got a positive slope. Okay. Now this is kind of an interesting one because the easiest number to test in this interval from 1 up to infinity, you can't test 1 itself, so test the next easiest number, which would be 2. If you plug 2 back into your derivative, 2 squared is 2 squared is 4. 4 times 3 is 12, so this is 12. But then this, when you plug 2 in, becomes negative 12. So 12 minus 12 is 0, but 0 plus 3 is positive 3. I get a positive number again, which means I get another increasing graph. This is kind of a weird one. I didn't really realize it until we got into it, but here's what actually ends up happening for this graph. This is a cubic graph, so it's an S-shaped curve. The value for 1, since 1 is the critical value, if you just kind of think about it, if you plug 1 back in here, you get 1 minus 3 plus 3, so that's 1, 1. Here's what this curve actually looks like. That's just a point of inflection right there at 1, 1. So what you'll notice is this graph is increasing from negative infinity to 1. And then at 1, it doesn't stop. It doesn't go back down. It just keeps increasing. That's why this curve, or that's why our increasing decreasing test shows that it's increasing at all points. So that was kind of a weird one because there was no change in direction. It didn't start going down at any point. It was increasing on both intervals. Okay? All right, we're gonna keep it moving here, and hopefully with these next two examples, we'll be able to get things pretty well figured out with how the parts of the test run. All right, the first thing we do is find the derivative. So here, this derivative is going to be found by doing the chain rule. You bring 2/3 down, leave the inside as it is, x squared minus 4, subtract 1 from the exponent, so you get negative 1/3, but then multiply that by the derivative of the inside, which is 2x. Like I said, we're just using our simple differentiation rules. So I'm going to write this, I'm going to clean this up. Here's my 2/3 in my fraction. This whole thing needs to move to the denominator, x squared minus 4 to the 1/3. And then I can put this 2x up top. So basically what I can do now is 2 times 2x on top. I can just rewrite that as 4x. There's my derivative. My derivative is 4x over 3 times x squared minus 4 to the 1/3. Okay? This one and the last one are both going to be fractions as far as their derivatives go. So to determine your critical numbers here, when it's a fraction especially, it's super easy. All you do is you figure out what numbers will make the top and or the bottom 0. So just look at the top. The top is 4x. What x value is going to make that top become 0? Well, it's obviously 0. 0 times 4 is 0. So x equals 0 is a critical number. Okay? Looking at the bottom and asking ourselves the same question. What x values will make the bottom 0? Well, the only thing that's going to make the bottom 0 is whatever x values I plug into x squared minus 4. So that would be 2. 2 squared is 4, 4 minus 4 is 0,